Hi, Philip.
Good morning,
Good
afternoon.
morning.
Good morning. How are you?
I'm doing well, keeping busy.
I would be surprised if you wouldn't.
Okay, but thank you for having some short break in between something.
No worries. I force my students in my green chemistry courses to do life cycle assessment. And they grumble and because it's a lot of work. And then at the end, they say, wow, we never realized that the product isolation causes more environmental harm than the actual synthesis. Now, chemical engineers know this already. 90% of a chemical plant is the separation, some purification, and 10% is the chemical reaction. And that's roughly what happens with the environmental harm as well. And so this is a big problem in green chemistry, because lots of researchers in green chemistry are trying to design or select molecules which are less harmful than the old ones. Can we find greener polymers? Can we find greener furans or greener whatever chemicals you're interested in? And they do this research by looking at the toxicity and the environmental harm and flammability of each chemical and choosing the one that causes the least harm. And that's wrong, in my opinion. That's completely wrong way to do it, because they're focusing only on the chemical and not how it's made. What about green? Which of these two options is green? Should we be making our organic products from biomass or from fossil fuels? Which of those options is the greener option? And the answer in most cases, not all, but most cases, is that it's greener to use the fossil fuels, not the biomass. And as a green chemist, I feel horrified by this answer. This is not the way it should be. It should be that biomass is the greener option, but in most cases, the life cycle assessments have shown that biomass is not actually the greener option for making organic products. Fossil fuels are. Why? Why is that the case? The biomass causes extra harm to the environment and to health because you have to remove water. And in fossil fuel conversion and production, you don't have to remove water, or at least not very much. So let me give you a couple of examples. If we take a look at making biodiesel from algae, you can grow algae in wastewater. You can collect the algae and dry it, and then get the lipids out and transesterify it with methanol and make your biodiesel. That sounds wonderfully green, but if you take a look at this data from a life cycle assessment, you can see that the energy consumption to make the biodiesel from algae, the total energy consumption is greater than the energy value of the biodiesel you get from it. So the conclusion to this part is that the energy requirement for water removal is so bad that we have to solve this problem. We have to bring down that energy requirement for water removal if we ever want biomass to compete with fossil fuels, or even be better than fossil fuels economically and environmentally. So this is a big crisis for biomass conversion. Not every single reaction. There's some reactions of biomass conversion where the product just precipitates out and everything's easy. So in those ones, okay, maybe the problem's not so bad. But in most reactions, I would say the removal of water contributes a major part of the energy cost and the environmental harm. So we have to fix this. We have to be able to find better ways to remove water from raw biomass, from slurries like algae, and from products, okay? And separating water from hydrophobic products is not so bad, but if it's somewhat hydrophilic, it's a lot harder. So I'm going to look particularly at that. How do you separate water from product, or product from water? You can do distillation, which is the classical way, and it takes way too much energy, so that's useless. Okay, per-evaporation takes too much energy, because again, you have to evaporate the water and the ethanol or whatever it is. And reverse osmosis is much lower in energy, but unfortunately, it lets small organic molecules go through the membrane, and so it doesn't work for things like ethanol. And it also doesn't work for higher concentrations. So you can only somewhat concentrate your solution. You can't isolate your product by reverse osmosis, so that's not useful. Forward osmosis, which I've worked on as well, is a little bit higher in energy costs, but it has a lot of the same problems as reverse osmosis. But now what we're doing instead, sorry, I just shouldn't have clicked one more time, is we're using a solid polymeric amine that when you remove the CO2, it becomes insoluble and you can precipitate it out and then redissolve it. And some of them work rather well. And so that allows us to skip the reverse osmosis step and save further energy. So does it save energy compared to distillation? Okay, here is the raw calculations. The life cycle assessment still in progress. This is the energy cost for distilling that water acetone mix, and here's the energy cost for the various energy consuming steps, not including pumping costs for our new process. So it looks like it has a good chance of having lower energy costs. But this is completely unoptimized. But we chemists, we're not the only people that have myopia. Other people have myopia too. And how does that affect, society and environmental impact? Have you ever been to a store where they don't offer plastic bags? They only offer paper bags because they're trying to protect the environment. This is a bag I got when I went grocery shopping in Paris a while ago. And it says, environment's at stake. We use biodegradable, recyclable paper and not plastic because we want to protect the environment, that kind of thing. And so if I asked you, why is paper harmful? Most people wouldn't know. But if I ask you, why is a plastic bag harmful? People would have answers. It doesn't decompose in the environment, right? When you throw it away, it lasts forever in the oceans, and turtles eat it thinking it's a jellyfish, and then, all this kind of problem. And so the public is well aware of the drawbacks of plastic bags and not the drawbacks of paper bags. And so this is what it looks like for the average consumer. Plastic bags cause a lot of harm and paper bags don't. And you notice what the consumer sees? The consumer sees the use stage and the disposal stage. It's just like the chemist myopia all over again, except now it's consumer myopia. Consumers only see the use stage and the disposal stage. Any technology that has a flaw in the manufacturing stage is not going to look so terrible to a consumer because they don't see that. And so if you take a look at the life cycle assessments of paper versus plastic bags, what you find out is the paper bags are actually worse. The harm of the paper bag happens in the production stage and is therefore invisible to the consumer. But the harm of the plastic bag happens right in front of the consumer's eyes. And so the plastic bag looks worse. That's why there's this popular myth that paper bags are less harmful than plastic bags because of consumer myopia. Now, I'm not trying to praise plastic bags. They do indeed have horrible problems in the environment. That's not the point of this. The point of this is that the paper bags are worse than the plastic bags, and that is not popularly recognized. So how do you fix consumer myopia? First thing is education about the entire life cycle of a product, and that has to be based upon not just celebrity opinions, but rather life cycle assessments. And so here's the life cycle assessment data for paper bags versus the plastic bags, and you can see the paper bag is worse in every impact than the plastic bag. And so this idea that paper bags are going to save the environment is a myth. Okay. So how do you educate the public? Well, that's where I've been doing this TikTok thing. So of course, right now, TikTok's getting a bad name because everybody thinks the Chinese government's spying on us. But I have been doing this TikTok thing, and I probably will continue. My channel is called Which is Greener, and I've been comparing these tables, like the life cycle assessment table you see on the left for paper versus plastic. But I can't show a numerical table because nobody's going to watch my videos. So what I do instead is I use my kitchen table as a table, and I show the paper bag, the plastic bag, and this is how much acid rain. This represents how much sulfuric acid is going into the atmosphere, representing acidification. Here's the amount of fertilizer, representing eutrophication of rivers, and I use balloons to show how much smog and how much red balloons for global warming. And this, I think, makes it a little more palatable than showing a table of numbers. First, we have to get better at removing water. If we want biomass conversion to take over from fossil fuel conversion as our default way of, getting feedstocks, we have to solve this water removal problem. Second, we all have myopia, whether we're chemists, chemical engineers, the public, life cycle assessment folks, all of us have myopia, and we have to recognize that and find ways to actively counteract that. And we can counteract our own myopia. We can use systems thinking, we can use life cycle thinking, we can use life cycle assessment including those unquantified impacts that are important to us. We can do this. And if you look at these bigger picture and look at the bigger system, it will change. It has changed my research, and it will change your research and how you conduct that research or your business or your life. Thank you very much for your attention, and I'd be happy to take any questions.
So the question is, so great talk, actually hearing this the second time. What about the equipment needed for these new better water separators with high pressure, the cost and energy consumption? Can you mention something about this? Did you?
Yeah, so the equipment needed for my process is conventional, like this kind of a pressure equipment is available already. If you use up to 10 bar of CO2, the energy cost, the capital cost is the same as for regular steel vessels. But if you go to like 40, 50 bar or 4 or 5 megapascals, then you're going to have thicker wall vessels, and it's going to increase the at least the capital cost, if not a little bit of the impact. But how do you accurately a biomass which is a waste stream from something? Okay, yeah. So when you're recycling something, there's 2 ways of doing the LCA. So let's say we're making our product from waste biomass. How do you allocate the harm, right? So one way is what's called cutoff method. So what you do is you say that, you know, let's say it's a waste from corn, okay? The corn is being sold for food, and we're taking the stover and we're going to convert it into something. One way is called cutoff. And what they do is they say that all the harm of producing the corn and the stover is blamed on the corn, okay? And then anything you make out of the stover, it gets none of that blame. So in other words, the stover, the waste is free of any harm, and the only harm comes from your conversion process. The other way of calculating it says that if that stover is actually going to be used for an economic process, it should share some of the harm of the original growing of the corn. And, you know, both techniques have advantages and disadvantages, but I don't know if either one is more correct than the other.
What would be, in your opinion, the room for non-aqueous solvents like ionic liquids and debiotic solvents in biomass conversion?
Yeah, it's a great question. There's lots of non-aqueous solvents like supercritical, there's ionic liquid, there's organic solvents. And the answer is the greenest solvent for any application is the solvent that makes the entire life cycle get minimized, right? So you could have one solvent that's horribly non-green, but if that solvent makes your process wonderfully efficient and all the other solvents make your process terrible, then maybe that one solvent that's not so green on the face of it is actually the green choice. So if you have a solvent that makes your process super efficient and super fast and easy separation, then it's got a really good chance of bringing down the total life cycle impact. And so hypothetically, ionic liquids, eutectic solvents, supercritical, all these other weird solvents could have wonderful roles to play. But you have to include the production of that solvent in the entire life cycle assessment calculation. And the classical ionic liquids like BMM, BF4, their syntheses are environmentally catastrophic. And so the recovery of the ionic liquid after every cycle has to be like 99.9%. It's some ridiculous fraction has to be recovered and recycled every time. Otherwise, the cost of them replacing the losses of the solvent end up being too harmful.
I think this was a really nice, a really inspiring talk, as I said before, and also, I mean, especially for students, but not only for students, to look a bit beyond what we are actually doing, and especially this, because as we're using a lot of building blocks that are made by fermentation, this is something to really take into consideration.
Can I? Oh, sorry, you didn't.
Yeah, go ahead.
Okay, it's just a small question. I would like to ask you what suggestions would you make for polymer chemistry start working on the field, because these happy hours has these lots of young researchers followers. So what do you suggest when you think about non-quantified inputs. So what to look for in the chemistry we are doing as a polymer scientists?
In terms of non-quantified impacts, is that what you said? Yeah, I think the polymer, I was talking last week with the head of the Canadian Coatings Association. Of course, they're a big market, coatings is a big market for polymers, and they are terrified. They're shaking in their boots, as the expression goes, because this ban on the single-use plastics for bags, they can see that the plastics that are used in coatings are also single-use plastics. And so they can see in the future some legislation coming down saying you cannot use single-use plastics for coatings, or you cannot use non-biodegradable plastics or non-recoverable plastics. And so they can see all sorts of legislative headaches coming their way.
It is a biodegradable polymer.
Yeah. So what we need, and we need polymer chemists and chemical engineers to be working on this as quickly as possible, because the industry is terrified. We need new ways to make polymers biodegradable. We want them to last long enough to protect the side of your house or whatever you're painting. But then after that application, we want it to break down as quickly as possible. And the current technology, if you look at the literature for making, polyacrylates and polymethacrylates and these kind of standard polymers, it's very little technology on how to make such chains with biodegradable linkages in them. And the technologies out there are kind of expensive. So this is an area of research that is desperately needed. So how do you make these polymers? How do you make replacements for nasty chemicals? I would recommend anybody who's starting out in a research career to take a look at LCAs and government databases on emissions. Canada and US and probably countries in Europe have these databases that are open to search on the web for, what's the greatest source of hexane emissions into the atmosphere? What's the greatest source of ethylene emissions in the atmosphere? You can check this and you can see what industry is emitting the most and how you can fix that. So I really think that guiding your research by looking for problems rather than looking for solutions is the best way to start out, right? If you're a polymer chemist, this issue of biodegradability, which is related to biomass conversion, but it's also a separate question, right? This is the biggest issue right now, and this is the biggest problem. So that's a great area to start doing research in.
Thank you. Really inspiring.
Thank you. All right.
Okay, I think there are no further questions. So I guess we would close the session.